You ever drive by one of those huge oil refineries, with all the pipes and towers, and just wonder, how does all of that not blow up? I mean, these places are packed with materials under incredible pressure and temperature. Well, in this explainer, we're going to pull back the curtain on the unseen shield that protects them and us. Let's dig in and see how it all works.
At the end of the day, it really all comes down to that one question. These plants are absolute marvels of engineering for sure, but they operate on a razor's edge. If you get it wrong, the consequences are, well, they're catastrophic. The answer isn't one single thing, but a whole layered system of foresight, physics, and some seriously precise engineering, all designed to handle the absolute worst-case scenario.
So, to get our heads around the danger here, I want you to think about a pressure cooker. You seal it up, you turn on the heat, and the pressure inside just builds and builds. Now, imagine that pressure cooker is the size of a building, and instead of soup, it's full of flammable or even toxic materials. Suddenly, you can see the scale of the challenge, right? And that brings us to the official term for this problem: overpressure. This is the big one. It's the specific enemy that engineers are constantly fighting. It's that critical moment where the pressure inside a vessel or a pipe tries to push past the limits of what it was built to withstand. If that line gets crossed, you get what they call a loss of containment, which is a polite way of saying a breach, a rupture, or an explosion. It is the one thing that absolutely must be prevented. So, here's the bottom line. Every single piece of equipment, from the tiniest pipe to the most massive tower, has a red line. It's called the maximum allowable accumulated pressure. The entire safety system, everything we're about to talk about, has one single solitary goal: to make sure the pressure never ever crosses that line. Now, if you want to build a system that's foolproof, you first have to imagine all the ways it could fail. This is where engineers almost have to be fortune tellers, thinking up every possible thing that could go wrong and lead to a dangerous buildup of pressure. And one of the biggest, most common scenarios they always plan for is an external fire. Just think about it. If a pool of flammable liquid catches fire right next to a giant tank, the heat is going to boil whatever's inside. That boiling creates a ton of vapor, and all that vapor means the pressure inside skyrockets. This is a classic, top-of-the-list worry for any safety design. But a fire, that's just the start. The list of things that can go wrong is pretty long. A valve could get closed by accident, blocking an outlet. A control system could go haywire and pump way too much material in. A simple power outage could shut down critical cooling systems. Or a tube could rupture inside a heat exchanger. And yeah, of course, you always have to account for plain old human error. Engineers have to plan for all of it. Okay, so you might be thinking, what if a fire starts at the exact same time the power fails? That's a fair question, and it gets us to a fundamental design rule called single jeopardy. The idea is that the system is engineered to handle any single credible failure. What it's not designed for is two completely unrelated disasters happening at the exact same moment. And look, this isn't just some casual guideline. It's written right into the industry's rulebook, API Standard 521, designing for what they call double jeopardy, like an operator closing the wrong valve at the same time a tube bursts, is considered so incredibly unlikely that it's just not a practical way to design things. The main point is, these systems are built to be incredibly tough against one bad thing at a time. All right, so we know what can go wrong. Now, how do we actually stop it? Well, the very first and most important line of defense is a surprisingly simple, purely mechanical device that acts as the ultimate safety net. The beauty of this thing is its simplicity. Let's just walk through it. When the pressure inside a vessel climbs and hits a specific preset limit, this device, usually a spring-loaded valve, is physically forced open. There are no computers, no electricity involved, just pure physics. It instantly vents all that excess pressure into a special set of pipes, and as soon as the pressure drops back to a safe level, that valve automatically slams shut. It's a really elegant, life-saving design. But just opening a valve and letting off steam isn't the whole story. You can't just vent a huge cloud of flammable or toxic gas into the middle of the plant. No way. That vented material has to be handled safely, and that's where its journey to the flare begins. A flare system is basically a plant-wide plumbing network just for emergencies. These massive pipes, called headers, collect the high-pressure gas from any relief valve that opens up and funnel it all to one safe, central spot, the flare stack. Way up at the flare tip, those gases are mixed with air and burned off in a controlled way, turning hazardous stuff into much less harmful things like carbon dioxide and water.
Now, I know this chart looks incredibly complex, and honestly, it is. But the takeaway here is actually pretty simple. To build a system that works perfectly every single time, engineers can't afford to guess. They have to use super precise data, like this chart, which helps them predict exactly how a liquid will flash into a vapor when it gets hot, to calculate the exact size of every pipe and every valve. It's that scientific rigor that makes sure the system can handle the massive rush of gas during an emergency.
So let's kind of zoom out and look at the whole picture as we wrap this up. It's not about one single gadget. It's a whole philosophy of defense in depth, an entire ecosystem of safety systems all working together, most of which you'd never even know were there.
It really starts with building tough, robust equipment in the first place. Then, it's all about anticipating every credible way it could fail. If one of those things happens, the automatic pressure relief devices are the first responders. And finally, the flare system gives all that dangerous pressure a safe place to go. The big idea is that safety isn't just an add-on. It's woven right into the DNA of the design from day one.
You know, these overpressure protection systems are a perfect example of the invisible engineering that our modern world relies on. It really makes you think, doesn't it? What other complex, unseen systems are out there silently working in the background, keeping everything from our power grids to our clean water running safely day in and day out?